Here's sac217 problem number 3. Got a long, straight, horizontal wire carrying 16.5 amperes northward. Just below that, we got a wire segment carrying some current northward, and we want the force exerted on the lower wire by the upper wire. Let's call northward into the page. So I'll be looking at this from the south. View from south. We'll have I1. That'll be the upper wire, carrying a current of 16.5 amperes. Now, if we're looking at this from the south, into the page is due northward. That's why I've got I1 to the north. And then I2, here's the wire segment, wire of length, call it L2, which is the 0.460 meters. And it's carrying a current, also northward, of 4.00 amperes. Now I've drawn these into the page. Out of the page would have worked as well, but I like north into the page, so when I draw the loops around this one, the magnetic field produced by this one, I can see where it passes through the lower piece of wire pretty easily. Now let's make sure we know which way is which. So this would be the upward direction, downward. If I'm looking northward, then east is to my right and west is to my left. So this is not like a map, because upward is that way and north is away from us. The magnetic field lines of this guy, this is what we're concerned about. Find the force exerted on this one by the magnetic field of this one. So I'm going to draw the magnetic field lines, or at least one of them, for current number 1. Now, to get the sense of the direction, I use the right-hand rule for something curly, something straight. Here the current is straight, and the magnetic field lines that it forms will be curly. So I point the thumb of my right hand in the direction of the current, and I find that the fingers, with the hand somewhat cupped, the fingers curl around in this direction. That is, the magnetic field due to this guy is in that direction. In particular, what's really important is the magnetic field at the location of this other wire, and it's due west. So B will be due west, B due to current number 1, so I could call that B1, at the location of wire number 2. So I'm going stepwise. I'm going to find the magnetic field produced by current number 1 at the location of wire number 2. And then I'll use the relationship between the force, the magnetic field, and the current of the victim to find the force on wire number 2. So step 1, find mag field due to I1 at the location of wire number 2. And we're using Ampere's law for that. From the formula sheet, we've got B is equal to mu 0, sorry about the noise, over 2 pi times I1 over R. That'll be B1, the magnetic field due to current number 1, at the location of wire number 2. So just substitute the values with units. This is 4 pi times 10 to the minus 7 Tesla meters per ampere times the I1. I'll go ahead and put the over 2 pi. I1 is 16.5 amperes. And the R here is the distance from the empty point in space. And yeah, there's something there, but think of it as an empty point in space while I'm just trying to find what B is. The distance from the empty point in space where you want to find the magnetic field due to the current and the wire that's producing the current. So I need this distance right here. And I'll call that R. In the problem, that distance is given as, the problem statement is given as 8 millimeters. So that would be 0.00800 meters. I've moved the decimal over 3 times because milli means times 10 to the minus third. So I've got 0.00800 meters. And substitute those values in, and I get for B1 0.0004125 Tesla. This is an intermediate result, so I am given an extra sig fig. I've got 4 sig figs here, and in the problem statement the values were given to 3, so in the end I got to round the final value off to 3 sig figs. Okay, now that I know what B1 is at this particular location, now I'm using the concept that a magnetic field exerts a force on a current-carrying conductor. Here, the current-carrying conductor, the victim is that wire segment that's carrying 4 amperes of current, and the exerter of the force is going to be B1, the magnetic field due to this guy up here, which we just found. Alright, the equation form of that concept, that a magnetic field exerts a force on a current-carrying conductor, is the force as a vector is equal to I L cross B, where L is the length of that wire segment that is the victim, the I is the current in the victim. I'm going to call this L2. And the B, the magnetic field, is the magnetic field that's exerting the force, which in this case is the B1, the magnetic field due to the first wire at the location of the second. And these B1 and L2, remember L2 is in the direction of I2. So up here, L2 is into the page, into the screen here, which is the northward direction. And B1 is to the left on the page, which is the westward direction. The two of them are at right angles. When they're at right angles, the cross product just boils down to the product of the magnitudes. In magnitude, the magnitude of the cross product, L2 cross B1 is just L2 B1. So in magnitude, L2 cross B1 is L2 B1. Let's work on the direction here, make sure we don't forget about it. This is a cross product. To get the direction, I use the right-hand rule for the cross product of 2 vectors. The first vector is L2, that's in the direction of I2, into the page. So I point the fingers of the right hand into the screen, in the direction right into the screen. Now, the plan is to make it so that when I close the fingers, they tend to point in the direction of B1. So I'll keep the hand straight with the fingers pointed in there. If I've got the palm facing leftward, I find if I close the fingers, they tend to point in the direction of B1, and the thumb is then pointing in the upward direction. So the direction of the force in this picture is toward the top of the screen, and indeed that is upward in the real world, because that's what toward the top of the screen represented in my picture. Toward the top of the screen is upward. So the force is going to be upward by the right-hand rule for the cross product of 2 vectors. And now the magnitude is given by that current which was 4 amperes. You can just see it up there. Times the 0.460 meters, and the B1 we found to be that many Tesla. And that yields 759 times 10 to the 6 newtons. Sorry, 10 to the minus 6. I got 0.000759 on my calculator. 759 times 10 to the minus 6 newtons, or at least I certainly want it to come out in newtons. Let's check this out. A Tesla is a newton per amp meter. And amp meter cancel out, and we are indeed left with newtons. So I can write the vector F has got a magnitude of 759 micronewtons and a direction toward the sky, upward. So that marks the end of SAC